Хорошо, тогда значит, у нас начинается доклад, который будет происходить на английском языке, но если кому-нибудь что-нибудь будет в целом понятно, что конкретно непонятно, то будет правильно, если... Что это? По-другому. Ну, не стесняйтесь задать вопрос по-русски, и мы разберемся тогда, в чем стоит ответ. Okay, so we can start, and this will be mostly in English, and then it will be not clear, people will ask you in Russian. We'll translate them.
Спасибо большое за предложение. Но извините, если я скажу по-английски, потому что вы слышите, почему.
Frankly speaking, it's much better than if you would speak French. I mean, English is better than French for us. So.
I hope that you will understand better. So, yes, I am a senior researcher. This year, I am a senior researcher in the Center of Poncelet at Independent University. And when I say this year, it's kind of complicated because of visa problems. So I will leave in 2 weeks and come back at spring. And during spring, I will be there for 3 months, and I will be very happy to speak with anyone about these subjects or other things. Because especially because today I will give mostly a survey and without many proofs and talk about many things, but so the topic is multidimensional symbolic dynamics. It's a topic which has emerged more or less in the last 10 or 15 years from the merge of some questions from dynamical system theory and some tools from theoretical computer science and logics. And the intersection has brought many interesting things. So first I will review, so when I say multidimensional, basically I mean 2-dimensional. But first I will quickly survey what happens in the case of 1-dimensional subshift of finite type, which I will define.
If you can pronounce more clearly what is SFT, what it stands for.
Yes, subshift of finite type, which I will explain what it is. And so we'll see some dynamical questions, and then we'll see computational aspect, even if the computational aspect already appears in the dynamical questions. So, we are given a finite set of symbols, which, for example, these 3 symbols, which form an alphabet, and we're interested in objects that we call configurations, which are by infinite sequence over this alphabet, or by infinite words, if you prefer. And so I will say that a pattern, a finite word appears in a configuration where, if you can see it, it appears. And a subshift, what is a subshift? It is a set of configuration that forbid some set of words, set F of words. Okay? So here I'm just given some list, possibly infinite, of finite words, and I will look at all bi-infinite words which avoid this list. And when the list of finite words can be taken to be finite, I will say that this is a subshift of finite type. For example, if you forbid this white word and the blue word, okay, it's just to be sure to be in this alphabet, but actually it's like taking a smaller alphabet. I forbid all white, and I can see in a window, in a finite window. Here I drew it with 3, but actually 2 is enough. I can check in parallel everywhere on the configuration whether I see any of these patterns, and in parallel I can check whether this configuration is in the subshift of finite time. So why is it called subshift? Because it's a name which comes from the dynamical system, and the motivation of this kind of object is encodings of dynamical systems. So imagine you have a space with a self-map, so often a compact space, compact metric space, and a self-map which is continuous, and you're interested in the iteration of this map. Then very often what we want to do in order to simplify the questions, or maybe to program, is to draw a partition of the space, a finite partition of the space, and then when I have an orbit of my self-map, of my dynamical system, I can encode it as an infinite word, which keeps some information about the system. Depending on the partition we choose, it can keep a lot of information, but often it's much simpler to study it. Yes?
Why do you use only 3 boxes?
It's example.
It's an example, sorry.
It wasn't that clear, but it's an example. But just a short comment to this. Actually, it's a very general and natural situation. You just measure something. You have something happening in the physical world. You divide all the space of possible locations, measurements, and then you measure to some. Yes.
It's one way infinite sequence.
Okay, and here if it's a self-map, a continuous self-map, you get a one-way infinite sequence. If you start from a homeomorphism, then you can get a bi-infinite sequence. Of course, the many things of symbolic dynamics, you can also study one-way infinite sequence. There are some little differences, but not very big. But yes, sorry, this is just an example. There were parentheses before, but I don't know what happened. And yes, so with this encoding, is there some fire or something? Did I say something wrong?
Может быть, fire, might be a fire.
Of course, yes.
But still, we need to, I mean, будет когда говорить, когда мы пойдем, пока мы здесь.
So,
Fire, but we don't care. Okay, so yes. So should I go on?
Yeah, go. So we measure something in discrete time and some in discrete space.
Yes. And with this encoding, you get something which is invariant by a shift, and which also, if you started from a compact space, which is closed. So it's shift invariant and closed, and actually shift invariant and closed in the product topology of the space is equivalent to the definition I gave here. Every shift invariant and closed set can be expressed as a set of configurations that avoid a list of finite patterns. Conversely. So there are many motivations from system theory. So from dynamical system theory, you can ask classical questions like, is there a finite periodic orbit, a dense orbit? What is the entropy? The entropy is a notion that more or less counts how complex the system goes in terms of or number of orbits up to some precision, to some time. You can even ask whether the system is empty, because it's not obvious at first whether you're given a list of finite patterns, whether you can always find a very infinite configuration. So here is an example. The example I gave before, you forbid only 2 white and maybe the blue if you want. And actually, this can be encoded as this graph. So when I see a white, sorry, it's the contrary, I got it wrong. You inverse the white and the yellow. So when you see a yellow, you can see anything after this, either white or yellow. But when you see a white, you have to see a yellow after it. So the set of configurations in your subshift are exactly the set of bi-infinite paths in this finite graph. And here is the matrix of the graph, which is also very relevant, because in this case we can easily answer all of these questions. There is a periodic orbit, clearly yes. It's a cycle in the graph. A dense orbit, it's a little less trivial, but they correspond to the bi-infinite paths that visits every finite path, that contain every finite path. The entropy is given by the logarithm of the largest eigenvalue of the matrix, which always exists by Pierre-Guillon's theory. Emptiness is even more trivial. Actually, if you remove all the vertices which don't have an outgoing edge, which are completely useless, then at the end the system is empty if and only if there is at least one vertex. So this is interesting because this is not a particular case. Actually, every subshift of finite type can be encoded in some sense on the graph, on some graph.
So, sorry, is it true that if we have a cycle, so we have a cycle if the subshift is not there?
So in this particular case, I'm not sure I heard your question, but in this particular case of one-dimensional subshift, periodicity and emptiness is more or less the same question, yes. You can see it because in finite graph, if you have at least one bi-infinite path, then you have one cycle. That's what you want. So yes, it sounds trivial when I say it like this, but it's to prepare what happens in the larger framework of that we are going to see. So yes, SFT are basically representable as finite graphs and matrices, and they also correspond to finite automata in some sense. In which sense? So let me now allow an alphabet projection. I have a subshift of finite type, and I can do some projection of alphabet symbol-wise at each position at the same time. And the class of subshifts that I obtain, I call them sophic. Some, I don't want to enter the details, but some subshifts are not subshifts of finite type. And the ones that can be, the subshifts that can be obtained like this by some kind of projection from SFT are exactly those which have a regular language. The language of a subshift is the set of finite patterns that appear in some configuration of the subshift. This is, I mean, if you're not used to it, it's very obvious from the representation by finite graphs. Okay, in some sense, we can say that one-dimensional SFT have the computational power of finite automata. Even if it's not exactly the same setting because we are in infinite configurations, but we can compare, we can do this comparison. Now, let's go to the two-dimensional case. So I wrote again some definitions. So basically, the configurations we're interested in look like this. It's infinite everywhere, of course. You have some colors. This is an example of alphabet. And you have some forbidden patterns. And the pattern now is not a finite one-dimensional word, but it's a finite pattern over some rectangle. It's a map from a rectangle to the alphabet. So, for example, here if I forbid blue, 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 yellow, and white blue, then and maybe white yellow, only horizontal patterns, then you are forced, this forces some kind of configuration in this way, where you have at most one line of blue and yellow on the left and white on the right. Maybe it's not exactly the set of patterns that I described, but I think you can get convinced that this family of configurations can be defined by some local patterns of size 2 times 1 and of size 1 times 2. So here the patterns of size 1 times 2 can force, for example, that in this example, that every configuration is vertically constant. The color is the same in all columns. Okay, this is a not very interesting example, but we can do more interesting things with subshift of finite time. Yes?
Why, in this case, the subshift is linear, not square? Not
so
why it is first?
Sorry. Yes. It's wrong. It's a Z2.
It's wrong.
It's sorry. You have the so there's a 2 here. Sorry.
Yes.
How could I miss
So
this?
And two stars means also 2 dimensions.
Sorry. Yes. This is the set of all rectangular patterns. I wanted to go fast. So it's linked to this notation comes from picture language theory. But sorry, I forgot the 2, which is probably the most important character in all the slides. So maybe that's why I didn't see it. The important thing is that you have this kind of shape here, and it's enough to look at just this window everywhere and to check that the whole configuration is in the subshift. So there is another representation, maybe a particular case of subshift of finite type is given by Wang tilings. So if I give you a set of tilings like this, I can say that the alphabet is this set, and the set of forbidden pattern is more or less obvious from the shape that I gave you. I just forbid, for example, this one to be under this one because it won't fit. Okay, it looks like it could nearly fit, but it doesn't. Okay, you understand? So you can clearly visually infer what it means, what the set of forbidden pattern is. I can put this on the right of this one, or this one on the right of itself also. So set of Wang tiles is an easy way to define at the same time an alphabet and the local constraints. And actually, all subshifts of finite type, in the same way as in one dimension, they could be encoded into sets of bi-infinite paths on a finite graph, all subshifts of finite type in 2 dimensions can be encoded in some way as a set of tilings obtained from one set of Wang tiles, one finite set of Wang tiles.
So,
yes?
I understand correctly, the example shows a set of tilings that restrict us from patterns of form 1 times 2 and 2 times 1 only. It's just only from such small patterns. Is it possible to restrict us from the larger patterns by providing some tilings?
Exactly. So you're right. This is an example of nearest neighbor subshift of finite type, which means that forbidden patterns are always of shape 1 times 2 or 2 times 1. But if you have bigger patterns, you can encode by doing some grouping of the information inside each tile. So in the same way as in 1 dimension, in the graph, the vertices of the graph could have some memory of some length n memory of what you have already read. here also, maybe this kind of left side, in this you can encode some kind of memory of all possible patterns around. I'm not getting too much into details. It's really not difficult. If you want to have the formal proof at the end, we can discuss. But it's some kind of encoding,
so yes. Do you mean that every snapshot file tab can be obtained as a projection of this block?
Yes.
So
Yes.
we can consider a large alphabet and then
yes.
project it in our table condition.
And the projection is globally bijective. So it's not locally bijective. So you have a projection from one tiles to. So if you want to start from any subsheet of finite type over, for example, this alphabet, then you're right. What is written here means there is a projection from some set of one tiles to these letters, like we saw before in the definition of speak. But here it's more than just a projection. It's a conjugacy in the sense that this projection, there is a bijection of the set of all possible two-dimensional configurations and their projections. There is exactly one pre-image of the. Yes, and we will see later that if you just say it's a projection, then you get the notion of Sophic subshift, like we said before, which is in some sense is yes, a projection of. We will see an example where it's not conjugated. Okay, so this is very nice to start doing some combinatorics and maybe some programming also, because you have a combinatorial structure. Of course, I put some stupid boundaries which are maybe complicated to enter in the program, but you all understood that you can also encode this as colors from an alphabet. So you have 4 colors around each tile, and you can do them if the colors match. But it's nice to write it like this also because it looks like a puzzle you can, a jigsaw puzzle that you can give to kids. And what can you ask them to do when you give this to kids? Or what can you do yourself? Or what can you ask the program to do? Well, first, I think every kid you're given these kind of things. I tried already, and they try to match them together and to form little patterns. Of course, little patterns may not tell us a lot about the infinite configurations, but it's also already a start. So, actually, given a list of forbidden patterns, or equivalently given a set of wrong tiles, you can write a semi-algorithm which tries to tile bigger and bigger squares. Okay? Because for each square there is only a finite number of tilings to try and finitely many matches to check. And this semi-algorithm will halt if there is some side of square where you cannot find any tiling. And if there is some size of square for which you cannot find any tiling, of course you cannot find an infinite configuration in the subsheet. So the subsheet is empty. But the converse is true, thanks to compactness or to Koenig's lemma, if you prefer. If there was no tiling, no infinite configuration, then there must be a finite square that you cannot tile. So this semi-algorithm answers exactly the emptiness of subshift, but it's only a semi-algorithm. It may continue forever. With a similar argument, we can prove that the language, which is similarly defined as in one dimension, the set of all patterns that appear in configurations of the subshift, the language is computationally enumerable, which means that there is a semi-algorithm which enumerates all valid patterns. There is a semi-algorithm which enumerates all invalid patterns. Because for a seminar, it's not exactly what is written here, because you have to forbid, when you find a big square where the tiling is not possible, then you have to forbid possible squares for which the only extension was this tiling. I don't enter too much into the detail, but still, it's not very difficult to prove that these subshifts of finite type have a co-computationally enumerable language, or co-recursively enumerable language, if you prefer. A second thing that kids or algorithms or computers can do is to try again to tile bigger and bigger squares, but this time by trying to keep the two vertical sides equal and the two horizontal sides equal. And why doing this? Because if I find a square with a valid tiling and the horizontal, this is horizontal, the two horizontal sides are tiled in the same, the colors on the top of the topmost line is equal to the colors on the bottom of the bottom line, and the same on left and right, then without having to tile by yourself the infinite plane, you know that it can be done because you can just copy this square into a periodic configuration. Okay? Yes?
But when we consider squares, we consider rectangles.
Yes.
With exactly the same property. And we would check that we have a periodic type, right?
Yes. You can also check for rectangles, but actually if you check only squares, it's enough, because if you have a rectangle period, with the least common multiple, you will find some. Yeah. So, yes. So, yes, conversely, if, exactly, it's a good remark, if, so with this definition of period, I even only ask one vector of periodicity. And here we find only configurations which have horizontal and vertical period. But it can be shown with a simple combinatorial argument, and a way of saying this is to say that configuration with one vector of periodicity behave more or less like a one-dimensional subshift, and one-dimensional SFT all have a period. So you build the second period, and actually you can show that every two-dimensional subshift of finite type with a configuration which is periodic in this definition, with one vector of periodicity, has also a configuration with two non-collinear vector of periodicity. And if you have two, it's also not very difficult to prove, since the set of periods is a subgroup. You can prove also there is a vertical and a horizontal period, and then at the end you can prove that there is exactly a square pattern that you can repeat. So this semi-algorithm halts if and only if there is a periodic configuration. So it's quite interesting. We have our two semi-algorithms. We can even run them in parallel. And one of them will halt if the subshift is empty, or if it contains a periodic configuration. So the only case where it doesn't help is if the subshift is non-empty and has no periodic configurations, which we call aperiodic. And this didn't happen in one dimension, so in one dimension or in many classes of subshifts, we are very happy with these two semi-algorithms. But now we will see that it's more complicated in the setting two-dimensional SFT. So, an example a little more complicated than the one we saw in the picture. When you have a cellular automaton is maybe yes. So you have a pattern here, a one-dimensional pattern, and you have a map from the patterns of this size to a new cell. This is called the cellular automaton if you apply it in parallel to the whole line. And here, we obtain a two-dimensional subshift of finite type if we apply this in every line. And
no, it's time, graphical, it's timeline.
Yes.
No, yes.
This is the space-time diagram of a cellular automaton. Of course, if I draw it like this, what appears in the space-time diagram of the cellular automaton is only the configurations which have an infinite history, also which can be extended, which can come back infinitely often. That's why I focus more or less on surjective cellular automata. But if we have any surjective cellular automata, this gives us an example of two-dimensional subshift of finite type. And surjective cellular automata are a computational model, which is Turing powerful, which is especially studied as a parallel computational model, because contrary to the Turing machine, computation can more or less appear more or less everywhere. But it can simulate Turing machine, and if I embed the halting problem of the Turing machine and I simulate by a cellular automaton, it gives me undecidability of some reachability problem on cellular automaton, whether a given cellular automaton can reach some particular state starting from a particular state. And if I look at what it gives me on the obtained two-dimensional subshift of finite type, it gives me undecidability of the following problem. Given a set of forbidden patterns, sorry, this should be a double star, a set of two-dimensional forbidden pattern, or equivalently a set of Monk tiles, and given a specific tile of the alphabet, can I extend this tile into a valid configuration? Or said differently, is this tile in the language? So I give you my one tile set, and I say, okay, do you think you can tile the whole plane starting with this particular? So it's not exactly the emptiness problem, but it's not very far. Okay, with the same arguments, if I embed a universal Turing machine in my simulation, I get some specific subshift of finite type with undecidable language. What does it mean? It means that I have a fixed set of long tiles, and it's undecidable whether, starting from some finite pattern, you will be able to extend it to tiling of the plane or not. But it's not yet the undecidability of the tiling problem. And actually, Wong, who defined the Wong tiles and who proved these quite not so complicated results, he conjectured that the emptiness of SFT was decidable. And it was disproved by his own student, Berger, some years later. So, as we saw before, any undecidability result, any proof of the undecidability of the emptiness problem requires an aperiodic subshift, because it must contradict my attempt of algorithm by doing the two semi-algorithms in parallel. So to start with, let's look at aperiodic tilings. I could spend hours describing them, but we don't have so much time. So this is a list of 3 most important families of SFTs which are aperiodic. So I wrote aperiodic tilings, but it's an aperiodic set of tilings. It's an aperiodic SFT each time. The first one was in the 60s, and all this family is based on the notion of substitution, which means you have an inflation rule which tells you that a letter can also represent a bigger square, and the same at each level. So this is a nice picture from Boulangier's construction. So the third one in chronological order is in some sense very close to the first one, in the sense that it's some kind of dual, because it's based on the notion of self-simulation. Self-simulation is, instead of having an inflation rule for letters, you have an interpretation of each big square as a unique letter. So it's actually very close, but in the way to apprehend the construction, the first one maybe is in some kind lets the tilings build more or less passively, and here it's more computational point of view where we enforce things actively. And it's nice to notice that in the construction by Durand machine correction, the notion of universal Turing machine and a computational notion is present since the beginning of the construction, even to prove just the existence of an aperiodic subshift of an attack, which is a result which doesn't involve computation. You need some computation, and really it's an important feature of the construction. So, and the second in chronological order family of construction is something which stimulates some piecewise, some space-time diagram of piecewise affine map. And probably Guillaume, who was in Moscow in the last month, is talked more about this in his seminar. All of these proofs, interestingly, they are necessary to prove undecidability of emptiness of SFT, but also it's interesting to see that all of these proofs very, very easily after proving aperiodic tilings, it can be proven undecidability of emptiness by just putting as another layer some space-time diagram of Turing machine on top of these aperiodic constructions. So maybe I have to go down. So, yes, let's go through some dynamical questions we had at the beginning. We asked about entropy. Entropy tells you more or less the growth of the number of finite patterns when you increase the size of the square. So you expect it to grow exponentially, and even exponential in an exponential of the square. That's why we divide by n squared. So this is finite. This is a limit thanks to some Fekete lemma. So it always exists. And dynamicists were asking, so we know exactly what are the entropies of the one-dimensional SFT. What are they in two dimensions? And actually the answer is quite interesting. The entropy are exactly the real numbers that are the limit of non-increasing computable sequences of rational. That has been proven some 10 years ago. So this kind of construction involves high-periodic tiling and computation everywhere inside the tiling. So I won't detail this.
So
Yes?
P10 is not all real numbers, right?
This is
For me, it's not obvious that it's not all positive.
it's countable because you have countably many computable sequences. So this is a countable set.
Yeah.
And then you can also have a hierarchy of such real numbers by taking limits of non-increasing of non-decreasing in different sections, and you can prove that the hierarchy doesn't collapse. And it's interesting to see where in the hierarchy lie your real numbers. So here there is a... So there are two things that are proven. First, that the number is always pi01. It's not so hard. There's a little trick to do with the limit. It's not direct from the definition. But the second thing is that for every real number which is positive, non-negative, you can build an SFT which realizes exactly this. So of course, this SFT will involve the machine, the Turing machine that is from the definition of this sequence. Now I have asked about periods before. So first thing, does there exist a periodic orbit? This problem given a finite set of local patterns, forbidden patterns. This problem is unresolvable. It's not very hard when you start from an aperiodic, when you know that there is an aperiodic subshift and you can embed space-time diagram in the Turing machine. Now, interestingly, also in the last 10 years, Jandel and Valier have characterized the set of slopes of these periodicity vectors. So
what is this Gurevich? Is this Yuri Gurevich?
Yuri Gurevich.
Just usual Gurevich.
Yes. I have always, I'm not sure how many Yuri Gurevich there are.
No, this one who was from Novosibirsk and who did logic.
So, yes, I think it's this one. So you have a periodicity vector here. You can be interested in the set of all periodicity vectors of one given SFT. This set is a computably enumerable subset of rationals. And for every computably enumerable subset of rationals, they managed to build a subshift of finite type, which has exactly this set as a set of slopes of directions of period.
How do we define a period of X? Is it any period or the smallest in some sense? Or
so here,
it sounds like periods should be somehow related one to each other.
Okay, sorry. Sorry, this is not very, you're right, this is not very formal, because here we require this to be the only direction of periodicity of the configuration.
Okay.
So we forget about the configurations which have two periods. I said before that if there is one, there are other configurations which have two, but still there are ones which have one, and we are interested in these ones.
But what is the set of all P1, P2, of all the ratios P1 divided by P2 if there is only one direction of period?
No, one direction per time. We have a fixed set of times, and we have multiple different timings.
So here I should add, sorry, maybe what should be true is P1, P2, P1, P2Z equals the stabilizer of X, okay? Instead of is in, I think this is the correct. So you don't have any other period for small x outside of this line. But for in capital X, you may have many x's with different periods, and I'm interested in this set, and it's any computably enumerable subset. They also proved that the set of horizontal period, this is a quicker, this means z times 0 and nz times 0. The horizontal line, I wrote the horizontal line as z. So the horizontal lines, the set of horizontal periods inside an SFT can be any set which is in n space of linear non-deterministic space. Here I wrote that subsets of integers are represented in unary. Okay, you represent in unary, and they showed that the necessary condition, which derives from the definition, is also a sufficient condition to be a set of horizontal periods. And for the sake of bi-periods, here we are interested in the configurations which have two periods.
There is n for which there exists n.
Sorry, this n is not the. No, this n is not.
There is n for which exists n.
X. Okay, sorry. This is x. N such that there exists x, which has exactly this period. And this is just linear. Sorry. So these links the dynamical questions not only to computability but also to complexity theory. If you are in a subsheet where you don't have periodic configurations, then you always have uniformly recurrent configurations, which are sometimes called almost periodic or quasi-periodic sometimes. Uniformly recurrent means that for every pattern, if I pick up one small pattern here, there is some window, some size of window, such that in every window, I will see at least one occurrence of this pattern, in every window of this size. So it's not far from periodicity, but it's not as regular. And there is a classical theorem in dynamical systems which says that you always have a uniformly recurrent. It can be periodic, but if you are aperiodic, it's not. In these aperiodic timings, for example, they are uniformly recurrent. And then you can ask this function of the size of the window depending on the size of the pattern you're looking for. How does it grow? And Bailey and Jordan have proved that it can be greater than any computable function. There are also characterizations of Medvedev and Mushnik degrees and sets of Turing degrees that you can find in SFT, but this requires some definitions, and maybe I won't spend too much time, so if you have questions on this, I can come back later. I just wanted to say something about how to interpret computation of subsheets of finite type. We said in the one-dimensional case, we said that we can interpret the subsheet of finite type as some kind of computational model, and the projection of alphabet as a process of computation, and the obtained subsheet as the result of the computation. Maybe in 2 dimensions, you can do first projection of alphabet, and then you can just keep one line of the subsheet of finite type. Sorry, one line of the suffix shift. After doing one projection of alphabet from your SFT, you get to a suffix shift, it's the definition. And from the suffix shift, you can take a trace, which is a one-dimensional subsheet. You can show easily it's still a subsheet. And it can be proven, and this is a big result which was proven in several steps, that the class of one-dimensional subsheets that you can obtain by these 2 simple operations from SFT is exactly the class of effective subsheet. Effective subsheet, what is it? Is the set of subsheets where the forbidden family of patterns is not finite, but it's not arbitrary. It's something that you can describe finitely by some algorithm. You can computably enumerate the forbidden pattern. So, in some sense, this computability theoretical definition coincides with a dynamical origin definition, which is traces of projections of subshift of finite type. And this can be a hint that subshift of finite type can really be considered as a computational model that is relevant and that is, in some sense, as powerful as Turing machine, even though in some sense it's even more powerful because it does this computation in parallel and everything. This result allowed Durand machine-code chain to recover another result of theirs, of Durand-Levinian chain, that you can find SFT where every configuration has a very complex, is very complex in the sense of sub-patterns and cohomology complexity. The cohomology complexity of every pattern that you find in every configuration is lower bounded by the size of the pattern.
Not n squared.
Not n squared, because I will say a word on this, because actually n squared is not, because this is the best one. Maybe I will skip this. You were asking about the projections of alphabets. So here I'm talking about suffix subsheets, and maybe your question before can be related to the question, is there a suffix subsheet which is not an SFT? So in general, what are suffix subsheets like? So here we saw that if we take a trace of a suffix subsheet, it can be any effective subsheet, and this is a necessarily sufficient condition. But if I keep the two-dimensional version of the computed object, the suffix subsheet, what do they look like? Can it be any two-dimensional effective subsheet? For example, here I take the subsheet over two symbols where I force at most one yellow, well, one white to appear. This is not a subsheet of finite type. It's not difficult to see that you cannot forbid only finitely many patterns, because otherwise you cannot forbid another of these to appear very far away. But it's so big, I just have to consider this super alphabet where blue is projected also to yellow. And I color in blue this quarter plane. And now the set of pictures which look like this can be defined by finitely many forbidden patterns. Because, in some sense, I have kept the information that my white cell has appeared. So here, this is a projection of an SFT over 3 letters. There are things that are less clear. For example, I interpret my binary configurations. So I define another subsheet. Interpret your binary configuration as a set of connected components of white, where connected means by 4 layers, for example. Then I can ask for the condition that all of these components have even cardinality. Maybe it's the case on this picture. I tried to. Is the set of such configurations defined by this, is it Sophic? Maybe we can take 15 minutes after the end of the talk if you're interested. It's not very hard to see that it's Sophic. But you have more complicated examples. If you have the same condition but odd instead of even, then it's much more involved. And we finally proved recently a larger result based on 3 automata, but it's not obvious at all when you just see the definition. And it's so little obvious that the corresponding questions in 3 dimensions are completely open.
So a gene is what?
Sorry?
Guillon.
Yes.
Means you.
Yes. Okay, this particular case was originally proved in by a non-published work of Julien Cassagne, but we proved a very large class of things that are defined by some automata language.
The type of trait that connected components are defined here.
So yes, maybe, so there are several variants of the problem. Here, the definition is the set of configurations such that all finite connected components of white have even cardinality.
And by the way, if the sets all such configurations that all white connected components are finite, is it static?
So in this case, it's not even a subshift, because it cannot be defined by any set of patterns. A way to see it is by the topological version of the definition of subshift. It has to be closed. A subshift has to be, no, sorry, any subshift has to be closed, which means that shift invariant and closed, which means that when you take a valid, a sequence of valid configurations, and any pattern which agrees with more and more, with a bigger and bigger square with your sequence, should be also in the same set. So you can build bigger and bigger finite components, and you will build infinite components. And by yes, but there is also a way to see that it's directly that it cannot be defined by forbidden patterns, but any set of forbidden patterns. And it's the same here. If I put equal instead of less than or equal, then it's not closed. So what are the necessary conditions for two-dimensional subshift? So we saw that they must have co-enumerable language. Actually, we saw this on SFT, but it's not difficult to see that it's preserved by projection. Also, there is a condition on infinitary communication complexity. If you give Alice this half of configuration and Bob this half of configuration, you cannot really directly apply communication complexity theory because they have infinite information. But instead of the number of bits, if you measure in terms of the entropy of the one-dimensional subshifts that you find here, then there is a nice infinitary communication complexity theory which allows you to say that since the subshift has to be a projection of a subshift of finite type, then Alice and Bob cannot share too much information with each other. So if they need to share too much information with each other in order to know whether the configuration is in the subshift, then the subshift is not Sophic. Example, you see this subshift, the subshift which is defined by a line of blue, and on the left of the line of blue, if the line of blue appears, maybe it doesn't appear in the configuration, but if it appears, you force the left part to be the symmetric of the right part. Then look at the number of patterns you can find here. Maybe it's exponential, it's exponential in n squared because you may have any pattern, any binary pattern. And so a way of seeing this is that two of such patterns must have a pre-image in the SFT which have the same boundary in the square, because this grows only in a linear exponential. And so there are two patterns that are interchangeable, but this will make a configuration which should not be accepted in this exception. I'm saying things very quickly because I don't want to enter into detail. The thing is, there is a strong definition, a strong constraint on effectively closed subshifts in two dimensions to be Sophic. This argument has been, yes, so it can also be seen as having a non-maximal Konrad complexity. This is the question you asked. You cannot get a squared exponential. You have to be a simple exponential in the Konrad complexity because you always have one pattern which is the smallest in lexicographical order with the, so I'm talking in SFT. In SFT, if you find one square like this, then that appears in the SFT, then there is a least, graphically, there is the smallest pattern that fits into this square. And this pattern has a description which is square.
Probably you meant order n, not to the order.
Yes, order n. Thank you. Order n because yes.
You just describe it, so you can just describe it by logarithms. You just describe n, and then you say this is the smallest.
No, because because you have to. You don't know which. You don't know which square is allowed. So the description is the tiling of the square. Is the word that you can read here in the border. It's not enough to have n because you don't know which square will be allowed. But if you say, okay, I have one square which is allowed of type n, and the boundary of this square is this, and you give a word of length for n, and then if you say there is a way to fill it, then there is clearly an algorithm which finds a way. This argument has been made more precise to work with columnar complexity in bounded time recently by Detum and who spoke in this room, I think. Maybe a dynamical version of this argument is to say that there is always a uniformly recurrent configuration such that the number of patterns that you can see everywhere does not grow double exponentially. And all of these conditions are not satisfied by every effective subshift, except the first one. So there are conditions to help to understand what are the subshifts, but still we are far to really understand. Maybe, yes, maybe I want just to, I have a question about what happens when you replace Z2 by any other group. So here is maybe not the free group. The free group, basically, I know what happens. In the free group, everything is decidable. Everything in the monadic second order logic will be decidable. And for every virtually free means that it's free group up to some finite index subgroup. But the question is, and this is a good candidate to be exactly the class where the SFT have decidable emptiness. So by this line, you know that this SFT have decidable emptiness. But is the converse true? Because I'm stating equivalence here. Is the converse true? Many people are working on this and finding more and more classes of groups where we can find a way to embed computation in SFT and to prove undecidability and emptiness. But we don't have the full answer yet.
What do you mean by monadic second order theory?
Yes.
What are the signatures? What are the?
So you basically look at the Kelly graph. So you have the relation of neighborhood.
Once again, there was always one.
Monadic second order theory.
Yes.
Значит, quantifier.
Yes. So you have one quantifier, and you at the beginning you have the relation, like in graphs, you have the relation of neighborhood. So in theory, it depends on the generating set. For unlinear groups, it doesn't. This is a conclusion. So SFT in one dimension have more or less the computational power of finite automata. In two dimensions have the computational of Turing machines, but they can be interesting as a model for parallel computation. Many dynamical properties that dynamicists use to answer in one dimension have undecidable answers in 2 dimensions, so the dynamicists were obliged to speak with theoretical computer scientists at some point. And maybe an interesting thing to notice is that most computational results that I stated have exactly a parallel similar result in the theory of finitely generated group, because subsheets are defined by finite patterns and how you can extend it, and it has the same flavor of construction as a finitely generated group. This is formalized as the notion of closure space. You can see, especially a paper by Robert, really makes this very formal, the parallel between the two theories. Among the open questions, I asked about relevant sufficient conditions to understand specificity of subshifts, of effective subshifts in 2 dimensions. For example, is there some condition on model of complexity in bounded time that implies that an effective subshift is Stochastic? I don't know. Maybe we can develop a little the complexity theory, because we have a nice computability theory in subshift, but we don't really know what complexity is, even though some results by Robert and Bagné take into account complexity. And this is the last question I asked just before: what happens in group? We don't even know in which groups can we build aperiodic subshift of finite type. By the way, just one sentence, because I find this funny. There is this question of when can we find an aperiodic subshift of finite type, in which groups? And Jean-Del has proved also that if the group does not have a decidable word problem, then you don't have an aperiodic subshift of finite type, which is also a strange result, because you have a hypothesis with computability theory, and you have a conclusion with something very natural to define in dynamics. So this is a way to see that the two are pretty much intricate, dynamics and computation in general. Thank you very much.
Если какие-то, два раза были потребовать, да? Окей. Давайте мы будем дальше. Есть ли какие-то вопросы?
У нас вопрос про то, почему является суффикс учетной конвенциональности.
Можешь написать по-английски?
No, there was a question about the subshift that consists of the even convection components. You promised that this was going to discuss that in 15 minutes.
No, I don't think we have 15 minutes.
So maybe
you can stay just.
Yes, if people who want to stay after the other questions, I can describe this. Yes.
Так, докладчик любезно согласился с вами отдельно. Yeah. Do you have any short questions, assuming short answers?
What about the larger dimensions, like 3-dimensional?
Okay, so in terms of computation, you cannot do that. You see that just by removing 1 dimension, you have full power of Turing machine. You cannot do better. You will always get effective subshifts by what I call the computation power. So most of what I described is understood also for other dimension, except this, the part where we start with very simple definitions, combinatorial definitions, but we don't know. But all the previous parts, which were like complete results in terms of computational power, we can do everything that is not possible, that is not obviously impossible. We can do it in 2D, so we can also do it in every dimension.
Еще вопросы? Ну, yes, if you start with, for example, live game, you can have 3D picture of what's happening. So, natural examples exist.
Yes, then in this case, if you start from a cellular automaton, a non-two-cell automaton, you don't have a periodicity. Except if you relax the definition of cellular automata by accepting explode to say that it's not defined. But yes, you have to run computation easily, and even in the case of light game, you have even a stronger form of computation, which is intrinsic computation.
Okay. So I think we have a really question. Yeah, no question.
Maybe a short question. You consider a grid of squares, so that you tile the plane with squares, but you can also tile the whole plane with triangles with the same, with all three equal sides, or with hexagons. Are there any analysis with the results? Or is it meaningful at all?
For computation, I think you can more or less, it's interesting. For computation, you can more or less do embeddings and it will work the same. Yes. And then you have interesting questions with respect to these things. And especially, yes, about hexagonal lattice, there is one very interesting question I have in mind, but maybe it's too long to explain it, but it's linked to the fact that your subshift can be seen as the space-time diagram of the cellular automaton in several directions. Then it can be interesting to see what happens when you see it in 3 directions, and there is something that we know cannot appear in Z2, in squares, but it's interesting to go in the hexagonal case, in that case, yes. But not directly for computation, for the same reason as in greater dimension, all the completeness result of computability, they are all the same.
Any more questions? No, I would like to thank first of all Pierre for speaking foreign language, and also the audience who are understanding foreign language and asking reasonable questions. And I think it was pretty understandable, even more than some of the talks we have here. So I think we are a very successful talk, and thank you very much for introduction to some topic, which is also in research in our department here, which is specifically important for us. So thank you very much. Насколько, значит, у нас, я хочу сделать объявление, у нас семинар предполагается быть каждые 2 недели, мы решили, что он будет регулярно происходить. И, по-видимому, в таком приоритете это внешние докладчики, в особенности иностранные докладчики, потом внешние докладчики, российские докладчики, которые все предлагаются искать, что может быть интересного послушать на главном семинаре, вот в смысле именно такого резюме результатов без доказательств. А дальше люди, которых вы хотели видеть у нас работающими, но которых до сих пор не взяли на работу, там, потом наши сотрудники и аспиранты. А если никто не найдется, то приглашаются, естественно, все члены кафедры, аспиранты и сотрудники по предложению членов кафедры. Но желательно, чтобы кто-то со стороны тоже к нам приходил и делал доклады. Yeah, this was an announcement that we appreciate people from other places, other countries and other universities to come and to speak at this seminar. Все, спасибо большое.